So while I'm waiting for the rest of everybody to show up, I'm going to probably also go through a little bit of the calculations for experiment 10, because I had a lot of questions in lab last night, and I want to kind of go through what it wants you to do as you're going down the columns for the vinegar analysis, because there are several steps to that.
I'm gonna get my book.
So I don't know if I don't think Dr. McHugh's class did experiment 10 except in terms of provided data. However, if you are provided data, you still may need to crunch the data. So this is one of the reasons why I wanted to go through that one, because it's sort of the one that we have devoted the least time to talking about the calculations for so far this month. And a reminder, there is a new discussion topic. Remember that you are supposed to make comments to 2 different discussion threads during the course of the semester. So this one's about NaNoWriMo. I don't know if you guys are particularly familiar with what NaNoWriMo is. National Novel Writing Month, something I'm involved in. And there's a lot of other people in Hampton Roads that are involved in that too.
Did you just go to the discussion board to do that? Because I would try to get up there and I didn't see any comments or where anybody said anything.
Yeah, it's supposed to be, if you click on the left-hand side of the page,
Yeah.
if you click on discussion, it should pop it open, and there's like 5 different discussion threads.
I'm gonna have to check again because I've been looking. You said something a couple of weeks ago about the same thing, and I went up there. I'm like,
I don't know if I can share the way it looks or not. Let me take a stab at this. I have to go find it on my page so that then I can show you what it looks like on the. All right, let's see if I can get Zoom to cooperate here. All right. Share screen. All right, so this is when you land on the lecture portion, and as you're going down the side here, it's got syllabus, announcements, modules, grades, discussions. If I click on discussions, okay, there's pinned. I didn't pin any of them, which just regulates which one appears at the top. And then if I scroll down, there are 1, 2, 3, 4, 5. There are 6 different threads. And then, for instance, the chemistry you can eat one, if I click on that one, it shows the picture that I posted, and I have about a half dozen people who made comments about that. So it should be, since it's saved and published, and various people actually made comments, it should be viewable.
Okay, I'll check it again.
As far as I know.
I'll check it again tonight. Thank you.
So let me talk a little bit about the vinegar analysis data. So I'm going to use the whiteboard on this. So one of the things that's true about the vinegar analysis is you should use the same concentration of sodium hydroxide that you calculated in experiment 9. Basically, it gets used 3 times. It gets used at the bottom of part A in experiment 9, which is when you do the average of your 2, basically you take your 2 trials and you average them together. Then you take that piece of data and you use it on the back for part B, and you use it again for doing the experiment 10 stuff. So experiment 10, same concentration. All right. If you used your flask in such a way that you just set it on the balance and made it go back to 0, you may not have a mass for the flask by itself or for the flask plus the vinegar, which is fine, as long as you have a mass for your vinegar, which is probably approximately 4.5 grams. Because if you used 0.15 molar as your ballpark, and the idea that we wanted to use about 15 milliliters out of your burette, that should give you something in the ballpark of 4.5 grams. So you will have an initial burette reading and you will have a final burette reading. So one of the things that it asks you is for volume of sodium hydroxide used. Actually, that's supposed to be an H, not a G. So that's going to be your final minus your initial. Because remember, as you are reading down your burette, your final value is always a larger number because it's closer to 50. Because 50 is, really almost at the dead bottom of your burette. And the initial is higher up, closer to the top of your burette. So you're not allowed to have a negative volume. Negative volumes aren't allowed. So minus initial should give you a positive volume. Then it's going to ask you about the molar concentration of your sodium hydroxide, which is basically why I said this is one of the things you need to sort of redo here. Let me draw a line here. There. Okay. It's the same one. So whichever thing you used when you were doing your experiment 9, carry it forward and put it in that blank that's kind of in between 2 columns. It'll then ask you moles of sodium hydroxide. This kind of goes back a couple of chapters. You need to convert your milliliters of used over to liters. So move your decimal place. Then you're going to multiply by your concentration. So what this does for you is it gives you a situation where you have liters times moles per liter. That way the liters cancel out and you are left with moles. We are then using an assumption. You have a 1-to-1 ratio of acid to base, because 1 acetic acid reacts with 1 sodium hydroxide. Therefore, you will have the same number of acid moles as your base moles. They should be identical numbers. It's going to ask you for a mass of acetic acid. And one of the things we looked at on the board was, okay, acetic acid has a molar mass of 60.05. So if you take moles of acid and you multiply by your 60.05, which is grams per mole, moles will cancel out and you'll be left with grams. And as you're nearing the bottom, then it will ask you for a percent by mass. So let's invent some data here. Let's say that your original sample of your vinegar weighed 5.1 grams, 5.100, because there's 3 decimal places on the balance. And if I had, let's say 0.412 grams of acetic acid. So now you have 2 pieces of data, and you can do 0.412 divided by 5.100. And that will give me 0.0807, and then I want a percentage, so times 100, and that would give me 8.07%. Things to keep in mind: if you are crunching the numbers for the vinegar sample that you did and you end up with less than 1%, be suspicious. Also, if you have more than 10%, be suspicious. Either one of those actually likely means you made a math error in your calculations. Because in order for it to qualify it as vinegar, you kind of have to have a certain amount, so that it has a little bit of noticeable acetic acid in it. But on the other hand, more than 10% starts to become really, really sharp for taste and potentially dangerous if you get too high. So greater than 10% is unlikely. So hopefully this will help you with the calculations for the experiment 10 information, which is due in a couple of weeks. Actually, for my group A people, it's due in about 6 days, I guess. Hopefully you're done by then. So questions about the calculations for that lab? Okay. I'm going to switch gears and go back to quantum theory stuff. So the last thing we were talking about prior to the test was the EM spectrum and my flaky little mnemonic device of Sig-Zuvermerl as a way to kind of wedge it in your brain of cosmic rays being at the shortest wavelength end of the spectrum, all the way down to radio and long waves at the bottom end. And I think the very last thing we talked about here was some calculations on how to use c, speed of light, and then lambda nu, our 2 little Greek symbols, lambda representing wavelength and nu representing frequency. So now we've got another kind of layer of information here. Once you kind of escape from the idea that EM radiation has to be waves, you begin to encounter another set of information that implies that it also can be considered packages or particles. We are going to dub those little particles photons. And I'll come back and talk about this again more later. If you're standing down at the beach, being that we all live in tidewater, if you're standing down at the beach looking out at the water, well, your human eyeballs see the waves, but if you had a nice scanning tunneling microscope, you could see the individual water molecules. Neither is untrue. Okay, both of them are variations of how to interpret the data of how it's made. Both of them play a part. So as we move toward talking about the particles end of it, some new words here. Energy in terms of atoms tends to be available in what is referred to as discrete units, also known as quantized. Think about money here in the US. Now, granted, your bank will quite generously give you 0.1% on your checking account for interest. But in terms of physical, actual money, if you want to hand somebody money, literally, the smallest item that you can give them in US currency is a penny. So our currency is quantized in pennies. Now, granted, you could give them more, you could give them $1, that's 100 pennies or more, but you can't give them less than a penny, not in US currency anyway, not in non-digital versions, if you want to actually hand them something for real, like hand to hand. So the idea of this quantized then also throws in another word here, which is a variation on a theme. This is known as the quantum. Quantum being one, because Latin. So quantum, one, quanta is more than one. And it's this little tiny amount of energy. Now, one of the things that's also true about a way to sort of think about this in terms of what your atom can either gain or lose, okay? You're walking up a flight of steps, kind of like layers in your atom. Well, you can't go up a half a step, okay? If you're looking at your staircase and you want to go up, you can go up one step, or, okay, if you're a little kid, you can go up one step at a time. If you're an adult, you can probably, without too much trouble, go up 2 steps at a time. If you have nice long legs, you might be able to stretch and go up 3 steps at a time. But you can't go up a half a step. You can't go up 2.5 steps because there's no place to put your foot to stand up on the 2.5 step. So that's kind of how the quantum idea works. You can gain or lose 1, 2, 3 more. You can't do them in halves or fractions of a quantum. There are lots of famous dead guys in this chapter, kind of like there were lots of famous dead guys back in the gas law chapter. One of the notable ones we're going to pick on for the moment here is Max Planck, Planck. He came up with a relationship idea in terms of an equation. So E for energy, in this case, the energy of the photon, can be calculated by Planck knew. Now, I don't know how to invoke a little crosshatch in my H on my keyboard. I'm sure that there might be a character variant for this, but what do they call it? The ASCII code. I didn't look it up when I was typing the notes. a lot of times you will see this lowercase h with a little crosshatch through the upper part of the H. And that is referred to as a Planck's constant. Lots of physics textbooks utilize this information too. And since in a previous equation, we saw C equals lambda nu. More variations on a theme here. You can calculate your energy by Planck times frequency, or you can calculate your energy by Planck times the speed of light and then divided by wavelength. A Planck's constant, or a Planck is often how they're just referred to as, is an awfully tiny piece of energy-based unit. Look at your exponent there. We've got 6.626 times 10 to the negative 34th. Now, the unit is joules times seconds. And truthfully, I probably should have put a little star, little asterisk in there to make it look more appropriately. Sometimes the textbooks just put the dot, kind of like when you're writing hydrate molecules, they use the dot. If you read physics information, they will often talk about tracing energy conversions all the way down to the Planck. So when we look at this number, we see all the way down to an amazingly tiny fraction of energy times seconds. This is how you trade info or trade energy in between the photons. An individual quantum, one quantum essentially, is 1 unit of Planck. This is how your photons are measured. They are some amount times the Planck. So we get this duality thing, okay? This is what in the 1920s/1930s, this was a very big point of contention between some of the physicists of the day, because half of them are running around going, no, no, no. If we're talking about EM, it has to be a wave. The other batch are like going, no, no, it's a particle. So there was this kind of argument back and forth. If you then compare those arguments to our modern day understanding, this is why it's called duality. Because back to that ocean wave idea, if you're looking at it on the macroscopic point of view, big picture, yeah, you're seeing the wave actions. If you're down at the ocean and you're looking at it with a scanning tunneling microscope or maybe an atomic force microscope, and you could actually see the molecules, well, the molecules are particles. Neither is untrue. It all depends upon how you want to use that information. So we'll spend a couple of moments here talking about the photoelectric effect. And this sounds like a really strange idea, and yet it works. If you shine a light on a metal surface, usually it has to be metal because it has to be something that is capable of letting its electrons go with a certain amount of ease. So if you shine a light, probably a bright light, on the metal surface, you can start bumping electrons off. Now it has a threshold, okay? If you have a wimpy light bulb and it doesn't have a lot of power to the light, the ability to bump those electrons off kind of doesn't happen? So think about if you have okay, I have a glass here sitting beside me, and my glass has a flat bottom to it. Okay. So if I have it sitting on a flat surface, if I nudge it with my hand or my elbow or something, if I nudge it just a little bit, it's probably not going to tip over, okay, because it has a relatively wide flat bottom here. On the other hand, if I hit it harder, basically more energy, yeah, I'll tip it over and spill my water. And the same kind of idea sort of plays in when we're talking about the photoelectric effect. There's some halfway decent pictures if you want to go back and look at the figures that are in your textbook, and it shows you the light beams, the photons, coming from the light, striking the surface, and bumping off the electrons. So now we get to take this a little bit further. Now we hit the infamous Mr. Einstein and his equation, E equals mc squared. So E is energy, M is mass. We've already seen C at the beginning of the chapter. C is speed of light. So mass times the speed of light squared is energy. So in a way, in an indirect way, you can say that energy has mass, since this is Hampton Roads. And we have aircraft carriers. And aircraft carriers are powered by nuclear reactors. One of the reasons that you can power something that big with a power source that's only about the size of a car is all about this equation. One tiny fraction of a gram can potentially generate kilojoules worth of energy. Because we've seen the speed of light number, 3 times 10 to the 8th meters per second as a value. If you square that, so we've got 9 times 10 to the 16th meters squared per second squared times grams, and a kilogram times meters squared per second squared is a joule. Some more variations on a theme. What if you wanted to figure out the wavelength of your particle that has a minute amount of mass? Well, now we're going to pull in Planck's constant again. M for mass, H, your Planck's constant, lambda, and C. So if you knew what your wavelength value was, since H and C don't change, they are both fixed values, you could calculate the mass, or you could do it in reverse. If you know the mass, you could calculate the wavelength. So all of this also is sometimes referred to as the de Broglie equation, more famous dead guys. Note, if you more variations, we've got lambda is H over mass times nu. You can also throw your frequency in to this equation. You might want to go back later, have a look at the bottom of page 291. There's some information there that kind of gives you some basic thoughts on how the de Broglie equation works on a more macroscopic scale. Because if we're talking about photons, oh yeah, it makes sense to talk about their wavelength. Talking about the wavelength of an object that you could actually pick up with your hand, like a baseball or a ping pong ball or something like that, that doesn't seem to make as much intuitive sense. And yet you could do such a calculation. So I kind of wish we had gas discharge tubes that I could show you. You might want to like look them up. I don't know if I can. Let's go back to this. Can I share my screen on Google? See if this cooperates or if it's going to give me a pain in the butt. Aha, maybe that'll work. Can you guys see the picture here of the gas-filled tube in the Wikipedia label? Okay, so if we look at these tubes that are glowing, look at the colors. Different tubes in that illustration are filled with different gases. So if I see if I can scoot this up a little bit. Actually, oh, it won't let me do that. Let me focus on that one. Okay, that one's a little bit better. So look at the one there on the top now. We've got the left-hand one, which is kind of orange-y with a little bit more yellow in the middle, and that's helium. Then we've got neon, literally neon. Hence, there is a reason why stereotypical neon lights are actually that shade of red-orange. And we've got argon, which is kind of purple. And then the last easily seeable one there is krypton. Krypton is kind of blue-ish. So gas discharge tubes are based upon the idea that if you pass electricity through a gas sample, you get energy input. You are increasing potential energy of the photons. All right, since we just passed Halloween about a week or so ago, if you ate lots of candy on Halloween, lots of sugar, it probably made you felt zippy for at least a few hours. And then eventually it wears out of your system and you kind of get the crash because potential energy may not be a permanent state of affairs. And this is true of your gas discharge tubes and your gas molecules or atoms within the tube. So you give them lots of energy. They're happy. They're bouncing around. They're also kind of unstable. So they package up their energy into the form of a photon and kick it out of the atom, which is in part why you see the colors. Different colors have different wavelengths, which also mean they have differing amounts of energy. Our little human eyeballs can see the visible spectrum from red all the way down to purple. So the edge of the infrared and a little bit of the near ultraviolet, and we see all the rainbowy colors in between. What's happening is your atom is passing from a high energy state, which is not stable, to a lower energy state. It may or may not be the lowest state yet, but when you get to the bottom, when you get to the bottom of the energy scale or the energy states, they refer to this as the ground state. I think the idea being that unless you're digging a hole, once you stand on the ground, you can't get lower than the ground. So I think this kind of goes together there. And then everything that is above the ground state ends up being referred to sort of collectively as the excited states. So one of the things that we looked at several chapters ago was particles within the atom. One of the things we talked about was how many protons, how many electrons, how many neutrons. So we're going to go back and pick on hydrogen here for a moment. Hydrogen is the bottom end, okay? If it's less than hydrogen, it's not actually an atom, okay? We've got one proton and one electron. But hydrogen is a gas, therefore we can put it in a gas discharge tube. We can add extra energy, but that extra energy doesn't hang around. And what you get is something referred to as an emission spectrum. Now look at the difference here. We've got the hydrogen spectrum, which isn't a rainbow. It's just these 4 or 5 stripes. We've got a shade of red at the far left-hand end. We've got kind of a purple, a sort of a bluish, kind of a green one, and then there's another red one at the far end there, at the far right-hand end. All those little tiny thin stripes are called a line spectrum, which is different from the absorption spectrum. The absorption spectrum often is dark slices in a rainbow. Well, why do we have stripes? Why don't we just have the rainbow? This goes back to the quantized idea. If you have packages of energy that are being kicked out of the hydrogen atom, it depends upon how much energy. If we think about the fact that we can't touch our sun for obvious reasons, but also because of distance, how do we know that the sun is made out of hydrogen and helium and a little bit of other stuff? This is why. They have looked at the emission spectrum through instrumentation and determined that the sun is mostly hydrogen, has a little helium, and has some token amounts of some other stuff too. But it's all about the quantization. If you actually look at the numerical values for the hydrogen, there are 4 designated ones that are usually referred to kind of sort of by name. They have 4 values that are listed there: 410, 434, 486, 656. This is known as the Rydberg series. You will also see it referred to as the Balmer series, Balmer. Both are just kind of variations on a theme. So kind of more back to whys. We're going to have a look here for a moment at this equation. We're not actually going to do all the calculations, but you need to know where it came from. So each one of those was a wavelength. 410 is a wavelength, 434 is a wavelength, etc. What if you did 1 over? Okay, 1 over a number obviously gives you a decimal. The way they calculated this was based upon the Rydberg constant, which is this really strange looking number that's 109.74 times 10 to the 7th meters to the -1 because it's a frequency number. And then in my little parentheses there, and I didn't have a way to make my parentheses longer so that it actually, the parentheses are actually supposed to encompass all of the fraction and not just the top half of the fraction, not just the numerator part. We've got N1 and N2. These are layers in the atom. So let's go old school for a moment. When you're in middle school and they first start talking about, here's what an atom looks like, and they start talking about this thing that kind of looks like a baby solar system. It's got the nucleus in the middle and it's got circles around it, which is loosely true in our modern understanding. This is all about the layers. Are you in the first layer if you're an electron? Are you in the second layer? Are you in the third layer? So Niels Bohr is one of those dudes from the 1920s, 1930s time period who began to put all the pieces together. He began to kind of integrate to a degree some of the wavelength information along with some of the particle information. And he put together a model for the hydrogen atom, which not only involves that equation, it also involves some other mathematical calculations too. So the idea then sort of gets supported by ground state, the not very excited state, is called level 1, also known as n equals 1. And then as you're climbing the staircase of energy, or layers of electrons, you get increasing numbers from 1 up to 7. 7 is the highest one you are allowed. Anything bigger than 7 is usually referred to as the infinity level. So take a slinky, okay? Take a slinky and make it go down your staircase. You know, it does that end over end over end thing. What if you're an electron? Your electron's kind of behaving like a slinky. As it goes down the staircase of energy, you can kick out electrons. Therefore, if you measure the wavelength, you can calculate energy. So all of these pieces are tied together. So Bohr was really ahead of the curve when he first started doing this. But then he ran into a roadblock. After he had done all the mathematical calculations for hydrogen, he's like, okay, let's up our game a notch. Let's do helium, because helium has 2 protons and 2 neutrons and 2 electrons. So he started trying to figure out all the math for the helium. And he couldn't get it to work. The observations of the wavelengths and all the things that he was doing at that period of time just didn't mesh. So he had buddies, Heisenberg and de Broglie and Schrödinger and his famous cat. So all of those famous dead guys are contributors to quantum theory, which is our modern understanding of how the atom is put together and how the electron layers work. So quantum theory is actually a whole slew of mathematical equations that describe the wave properties of electrons, but you can also extrapolate it to some other little tiny things too, other things that are subatomic. So let me talk about Mr. Schrodinger and his infamous cat. So in the world of quantum physics, quantum reality, things are not as predictable as you would think they should be based upon our normal everyday macroscopic world. If you put the cat in the box and the box is closed, therefore, technically speaking, until you open the box, both possibilities exist. One reality where the cat is alive and one reality where the cat is dead. Both of them exist concurrently until you perform the observation. So now we get to really, really bad physics jokes. So Mr. Schrodinger is driving down the highway at a high rate of speed, and he gets pulled over by a cop. And the cop goes, "Do you know how fast you were going?" He's like, "Oh, yeah, I know, I was going kind of fast." And as he's doing this, he keeps looking backward at the trunk, which makes the cop suspicious. So he decides that he should ask Mr. Schrodinger about why he keeps looking backward. And so Mr. Schrodinger, why do you keep looking back toward your trunk? Well, I have a cat. Why is your cat in the trunk? Well, because he's part of my experiment. So the cop asks Mr. Schrodinger to get out of the car, and they go around to the back of the car and open up the trunk. And he goes, "The cat is dead." And at which point Schrodinger says, "Well, he now is." Okay, the idea being that until observation occurs, both possibilities exist, which doesn't sound logical, even remotely, if you're talking about our macroscopic world. If I took my glass of water and I drop it, okay, it will fall and hit the ground and make a mess. In quantum reality, in subatomic space, more than one thing can happen. You have unpredictability. So we're going to throw this into something that is referred to as the wave mechanical model. More fun Greek letters. This one is called a psi. It kind of looks like a capital letter Y, except the slash goes all the way through from top to bottom. If you go back and look at some more pictures in your textbook, electrons are sometimes described as a standing wave. Think of it more like a snapshot of a wave. When you took the picture, it wasn't moving. So Bohr, in his original game plan, was, oh, well, okay, we've got a nucleus in the middle and we've got electrons around the outside. So they must operate like the solar system. You know, you have an orbit and your electrons fly around the nucleus in nice little predictable circles. That's not really true. Schrodinger expanded the idea. And we're going to change the ending of the word. Instead of calling it orbit, we're going to call it an orbital. And an orbital is a 3D probability map. So now we bring in Mr. Heisenberg. And this is a paraphrasing of his uncertainty principle. It is not possible to know exactly where an electron is and how fast it's going at the same time. Okay, more kind of ways to wrap your brain around this. We're leaving summertime. Is now the time of the year when all of the fireflies, lightning bugs are sort of going dormant, unlike the summertime where you can see them in your bushes. And if you're a little kid with a peanut butter jar, which is what I did when I was a kid, of course, this was back in the dark ages when actually peanut butter jars were glass. When I was a kid, and my little brother, my mother would give us a peanut butter jar with holes punctured in the lid with a nail, little holes. And you run around the front yard and you catch lightning bugs. You put them in the jar and you put the lid back on. And it has holes punctured in the lid so that they don't suffocate. So think about your firefly inside the jar. If you're standing in a dark area and he does his little blink, a few seconds elapse, and then he blinks again, but he's in a different place. Well, you know he was at point 1, and you know he was at point 2, but you don't know how fast he flew in between. Did he go really fast for a couple of inches and then he slowed down and walked the rest of the way? Or did he amble his way from one side of the jar to the other side of the jar in the 3 seconds that elapsed? You don't know because you can't see it. Now, what if you're really gentle? What if you take your lightning bug out of the jar and you put it in the palm of your hand and you touch your finger on the top of the lightning bug and don't squish him? Well, now he's sort of stuck, okay? He's sitting there wiggling. Well, you know exactly where he is because you're touching him. But he's not going anywhere because you're touching him. This is sort of a way to wrap your brain around the idea of why we can't know both pieces of data at the same time. If you know exactly where it is, chances are you've done something to alter the particle. On the other hand, if you measure how fast it's going from point A to point B, chances are you couldn't make accurate measurements in between point A and point B. So all of this is about these tiny, tiny, tiny particles. So let's talk about the evolution of atomic theory. So we've kind of seen all these people. We started chapter 2 talking a little bit about Democritus and his buddy Lysippos, who said, atom atom is the smallest thing you possibly can have. It's indivisible, meaning you can't cut it into pieces. End of story. Then there was Dalton. Okay, now we're up to the 1800s. He expanded the idea just a little bit. He still had the solid and indivisible idea, and he kind of refined the idea just a little bit to say, okay, you can't make it or break it. He and his buddy Lavoisier. Then we got to the almost end of the 1800s, and J.J. Thomson and his cathode ray tubes, which actually began to give the information that allowed us to know there are things smaller than the atom. There's positive bits and there's negative bits. Hence the plum pudding theory. Then there was his buddy Rutherford, roughly 10 years later, who was firing the alpha particles at the lead and the gold foil. He's the one who discovered the nucleus. So now we haven't got plum pudding theory anymore. Now we've actually got a nucleus And we know the electrons are on the outside, but that's about as much as we know. Go forward another handful of years. We hit Niels Bohr. He begins to discover there is actually something of an organizational pattern to those electrons. And he thought it looked like our little solar system. But then we start to hit the quantum theory era. Schrodinger and all his buds. And we realized that it's not really nice little circles. It's fuzzy because it's probability. Okay? If you have dice in your hand, 6-sided dice, so one different number of dots on each side, if you roll a pair of dice, there is a 1 in 6 chance for each one of those that they will come up a certain value. You have a less chance based upon math and probability. For instance, if you want to roll snake eyes, okay, if you want to roll 2 1s, that's less probable to roll 2 1s at the same time, because 1/6 times 1/6. Quantum theory is another whole level of calculations beyond that, but it still is calculations. We can make math equations that will allow us to figure out where it is probable that electrons will be and where it is less probable. All right, let's go back to the firefly in the jar, because this gives us another way to approach quantum reality. So the firefly is macroscopic. You could hold him gently between your fingers. You can touch him. The jar you've been containing him in for a while is a physical item. It has a lid, and you can take off the lid and put him in and put the lid back on. In quantum reality, the firefly could pass through the wall of the jar and escape. Okay, that sounds like, okay. In quantum reality, I could walk through a door without opening it, because there is a level of unpredictability. So let me end this with a couple of quotes. So this is pre-World War II. This is when Einstein was still doing his patent work stuff. Einstein was not fond of what at that point was the evolving nature of quantum theory, because in his calculations and his opinions, one of the things he said was, God does not play dice with the universe. He thought that we just had not mastered the math in order to do the calculations yet. He was kind of partially right, but also partially wrong. Our generation's version of Einstein was Stephen Hawking, who passed away just a couple of years ago. Stephen Hawking was a master of both cosmology and quantum theory. And his rebuttal to the original statement by Einstein was, not only does God play dice with the universe, sometimes he throws them where it cannot be seen. So as we dig deeper and deeper into quantum reality and quantum theory, we discover that things are a lot less predictable on this tiny subatomic scale than we originally understood. So the latter portion of this chapter focuses on how to describe the areas where electrons are likely to be and the patterns that we can organize those areas, which are called the Aufbau. Nice little German word there. And some other patterning that occurs at the end of the chapter about how we can use the periodic table to look at patterns in atomic size, electronegativity, ionic size, and several other items that are kind of related to that. So we've only gotten about halfway through this chapter. We will continue onward with this on Thursday, but you might want to start looking just a little bit at the homework set so that you know what is up and coming, and we will continue onward then with quantum theory on Thursday and possibly on into next Tuesday. Questions, either about lecture or lab?
Do you know when our tests will be finished graded?
Maybe tomorrow. I have about half of them done. I graded a few of them last night. I graded some of them this afternoon. I probably will grade a couple more tonight and the last chunk probably tomorrow afternoon. So they should definitely be done before Thursday. I'm working on it. Grading online is just painful. It just is. Grading stuff digitally is because I can't just flip pages. I have to scroll and yeah, just my annoyances on my end of the equation. Other questions? All right, I will see you on Thursday and we will continue onward with some quantum reality stuff.